solid dielectric. So first of all, the solid dielectric materials are used in almost all the electrical operators. If you look at that, the visible insulators or dielectric medium which we make use in a power system are solid, right? So we can see that it could be paper, it could be wood, rubber, mica, glass, porcelain, epoxy resin. There are many things. So which is visibly, which we can easily visualize, that is of almost all a solid dielectrics here. Okay. So whenever these electrical operators are connected with the solid dielectric material, so it has to be insulated current carrying part. So obviously, if you take your suspension insulator or pin insulator or disc insulator, which will be protecting your current carrying conductor from the other conductor or other different operating voltages. So a good dielectric should have low dielectric loss. The losses should be less here, and high mechanical strength because it has to hold many loads in the power system. Sometimes it could be any equipment, any operators, cables, transmission lines, right? Cables over there. So in many other part, it has to have very good mechanical strength over there, and should be free from any gaseous inclusion. So there should be no mixture of gases there, and moisture. It should be free from the moisture content. Okay, it should not easily ingress the moisture into that solid dielectric because it will lead to like any deterioration of your insulating material, and should be resistance of high thermal characteristics here. So it has to withstand very high temperature, and it should also withstand chemical deterioration because of any form of chemical. If it is exposed, it should not deteriorate. So that is also very important. So solid dielectric have higher breakdown strength compared to your liquid as well as the gases. The breakdown strength is very higher because of the few characteristics, so that we can see in the coming slides. So basically these solid insulating materials are of two types, organic type and inorganic type. So in organic we have example like paper, wood and rubber, and mica, glass, porcelain and epoxy resin in a inorganic material. So the breakdown phenomena in a solid dielectric will be of different, which has been classified into different types. How this breakdown will occur within a solid, the mechanism will be explained with respect to these things. The first one is intrinsic or ionic breakdown, is to say, then electromechanical, thermal, failure due to treeing and tracking, electrochemical, breakdown due to internal discharge. So among these, if you look at many question paper, so there is a repeated of questions is happening. So they will ask, explain intrinsic or electrochemical or electromechanical or thermal, or within intrinsic we have another called as a avalanche breakdown. So these many times they have been asked as a short note. So try to study almost all the things here. Very important thing are here. That is first one, second, third and fourth. Okay. So these four are very important. If you look at a question paper, you can see these questions over there. So here, among this breakdown strength, if you try to determine the breakdown strength of any solid dielectric medium, if you look at here, so where the intrinsic and the electromechanical breakdown mechanism is having very high breakdown strength, so which is at a very peak. So where the breakdown strength will be very high with respect to this mechanism. So whereas the next comes the streamers mechanism, that is also called as avalanche, and thermal breakdown and erosion and electrochemical breakdown, which has very least breakdown strength here. Okay, so we'll see one by one what all the things this mechanism will explain with respect to the solid dielectric. So basically the intrinsic breakdown, so whenever you apply any voltage of a short duration, which is of order of 10 to the power of minus 8 second, then the dielectric strength of a solid dielectric will increase very rapidly, okay, to a upper limit which is called as a intrinsic electric strength. So when you apply a short duration of this, the dielectric strength will increase very rapidly to the maximum limit or upper limit, which is called as a intrinsic electric strength, which you have seen in the previous graph. That was a intrinsic breakdown strength, that is the upper limit. So it was been done with some experimental here. So to understand how this breakdown strength can be, or breakdown mechanism, the solid dielectric will be explained with respect to the intrinsic breakdown. So where the highest dielectric strength is achieved only under best experimental condition when all the external influences has been isolated. If any moisture content or any damages or any other parameters which is affecting temperature, so everything has been removed here, which has been isolated. They have done an experiment by removing all the outer external influences has been removed and the test has been done. And it has been found that the value depends only on the structure of the material and the temperature. It depends upon the what type of structure of the material it is and what is the temperature. So purely the dielectric strength is based on these two parameters here. And the maximum electrical strength recorded in this test was 15 million volts. It's not milli, it should be million. It's a capital M. Okay. So millivolts, megavolts per centimeter. Or for polyvinyl alcohol, where the temperature, the highest temperature for the solid breakdown was with respect to this polyvinyl alcohol dielectric material, which was 196 degrees Celsius. So this intrinsic breakdown depends upon the presence of free electrons which are capable of migrating through the lattice of the dielectric. So these free electrons which are present within the solid particle, what happens? Usually a small number of conducting electrons are present within the dielectric part. Very small amount of conducting part will be present over there. So this free electron will be present over there along with the some structural imperfection and small amount of impurities. So these free electrons will be with a wherever we have a structural imperfection, if any damages, any cracks is happening, or any small amount of impurities are present, so where these free electrons will be along with these things. So these impurities, the impurities nothing but it could be any damages or any partial discharge which is within the insulator. If any impurities, atoms or molecules which have been within the solid dielectric, then the certain range of electric field and temperature will drop down here. So your breakdown strength will reduce whenever with respect to temperature, with respect to your electric field here. If you increase the voltage, then the breakdown strength will drop down. So based on this, this principle has been, there are two types of intrinsic breakdown mechanism based on these two. So the first one is called as a electronic breakdown and avalanche or streamer breakdown. So this one, the second one is avalanche or streamer breakdown. The first one is electronic breakdown, or I can write it here. So this intrinsic breakdown has been explained with respect to two mechanisms. The first one is electronic breakdown. The second one, which you see in the next slide. Okay. So this electronic breakdown, so within the intrinsic breakdown, which occurs when the time duration of order of 10 to the power of -8 seconds, and therefore it assumed to be electronic in nature, right? The intrinsic breakdown occur with a time of order of 10 to the power of 8 seconds. So and therefore it is assumed to be electronic in nature. So because of that duration, and the initial density of this conduction of free electrons is assumed to be a large. So when you apply a voltage, the conduction channel will be created. So at that time, the free electrons will be very huge amount of free electrons charges will be present over there. So and this electron to electron collision also will occur. So because of more number of free electrons, these electrons and electrons will collide each other over there. That is called as a electron breakdown. Because of this collide of the electron itself, the breakdown will occur. That is called as a electronic breakdown. The second one is called as a avalanche or streamers breakdown. So this is almost similar to our cumulative ionization, which you have seen in the breakdown of gases with respect to thousands second ionization coefficient. So we have been studied in the second ionization coefficient. There was a extra ionization present due to the bombardment of electrons over the cathode surface. So that is n plus electron we used to say. So that is where we say cumulative ionization. So here the conduction of electron gains sufficient energy above the certain critical electric field and causes liberation of electrons from the lattices of atom by collision. So the previous case I said that initially there will be more free number of electrons. So that free electrons will collide and will get a discharge, that was a electron breakdown. So what happens in this? So this will lead to the streamers breakdown. So streamers will explain that. So they will create a conduction channel within the two electrodes. If you take a cathode and anode electrode, so they will create a conduction channel. How it will conduct a channel, that has been explained by this Avalanche. Okay. So here under, if you take a uniform field condition, if I'm taking a uniform field condition, mean to say if I'm taking a plane to plane electrode and I'm applying a voltage with respect to this. Okay, I'm not considering any non-uniform field. Under a uniform field condition, if the electrons are embedded in the specimen, breakdown will occur when electron avalanche bridges the electron gap. So there will be a channel will be created so that electrons will flow from the anode to cathode very easily. That is called as the bridges of electron gap. So an electron within this dielectric starting from the cathode will drift towards the anode. So from the cathode it will move to the anode. During this motion it gains energy from the field and loses its during the collision. So it will gain the energy during the motion, that is from movement from cathode to anode. Whenever it get a collision with respect to electrons on the cathode surface, what happens? It loses its strength over there. The energy will be lose here. When this energy will be gained by the electrons which exceeds the lattice ionization potential, then what happens? The electrons will be liberated due to the collision of the first electron. So whenever the electrons will hit the anode surface, whenever this first electron will collide, due to that the electrons will be liberated. So this process will keep on repeat till the cathode, all the electrons reaches the cathode surface, or the conduction channel will be created. The bridge, the gap will be bridged between the cathode and anode surface. So this can be explained very easily from the figure where they have been considered a point to plane electrode. So here I was talking about a uniform field. They have considered a point and a plane electrode. So what happens within the non-uniform field and how this channel will be created, the avalanche will be created, that has been explained with respect to this diagram. So this is a point here, this part where when you apply a voltage between point and plane, so before reaching the plane electrode, if the voltage is applied between this, okay. So point and plane, this is a plane electrode, okay, and this is a point electrode. So look at here how the gap will be bridged here. So the free electrons keep on collide. So this is how the path will be created until it reaches the other part of the electrode. So this is a breakdown channel between point plane electrode with a radius of almost all 0.01 inches, 0.01 inches radius, and the thickness of this electrodes was being considered as a 0.19 inches. And the total number of impulse, and they have been applied an impulse voltage with respect to this. The voltage applied here was impulse voltage. Impulse voltage was been applied. And so this is how the conduction channel will be created with respect to the free electrons whenever it get collide with each other, or whenever it give rise to the new electron within that. So this is called as a avalanche or streamers breakdown. So don't get confused when it has been asked the streamers breakdown. Look at the question properly. Okay, in a final exam point of view, because in many question paper it has been said that streamers theory will explain about your gaseous also as well as the solid dielectric also, both. Okay, in exam they will specify if it is given anyone, they will specify whether it is a liquid or whether it is a solid. If it is a liquid, we know, sorry, if it is a gaseous, we know how the conduction channel will be created, and we have seen few equations, their streamer theory. So here have been considered a few drawbacks of 1000 theory that we need to highlight over there. So here it will explain just how the channel will be created from a anode to cathode with respect to avalanche breakdown. Okay. So the next one is electromechanical breakdown. So when if you consider solid dielectric, when it is subjected to high electric field, when I am applying a very high electric field for any solid dielectric, then the failure occurs due to electrostatic compressive forces which can exceed the mechanical compressive strength. So whenever this case happen, then the failure will occur within a solid dielectric. If you take a thickness of the specimen, if I am taking a thickness of any insulating material, that is a solid dielectric material, then let us be the thickness should be D naught, and it is compressed to a thickness D under the applied voltage V. So when we going with a high electric field voltage, what happen? This thickness D naught will be compressed to a D. When electrically developed compressive stress is given by the equation epsilon naught into epsilon r V square divided by 2D square. That is also equal to capital Y ln of D naught by D. So where capital Y is nothing but a Young's modulus, and it is, if we can simplify that equation with respect to V square, where V square will be equal to, which will be given, that is a voltage high electric field or high electric field strength which is applied to any solid dielectric medium which is given by the equation. And usually the ratio of your specimen thickness to the compressed thickness will be 1.67. Okay, and the maximum electric stress or the highest electric stress before breakdown will be given by the equation E max. So that will be V divided by D naught, or we can also write that is equal to 0.6 into Y divided by epsilon into epsilon r to the power of 1 by 2. So that will give the what is the maximum dielectric strength before breakdown it can withstand. So this equation is approximately depends upon your Young's modular Y and also the mechanical stress here. What mechanical stress is gonna overcome when it is compressing with the thickness with respect to the any given specimen here. And also when the material is subjected to high dielectric strength or high stress, the theory of elasticity does not hold good, and the plastic deformation has to be considered, because of there will be a variation of thickness of the dielectric will gonna vary. So hence we cannot make use of a property which is nothing but elasticity property. We have to take a plastic deformation has to be considered here. So this is regarding electromechanical breakdown. So this question has been asked many times. If you remember this equation and if you explain with respect to this equation, that will be sufficient. So in the textbook also nothing else is given apart from the equations. Okay. So highlight that which equation, what it is stating. Okay, and explain what it is happening in a electromechanical breakdown. So next we have thermal breakdown. So here the breakdown voltage of a solid dielectric should increase with its thickness. Okay, if the thickness of a solid dielectric is increasing, then the breakdown voltage also should increase here. Okay, so when the electric field is applied to a dielectric, then the conduction current, however small it may be, flows through the material. Okay, so that is because of the damages, very high voltages when you apply. What happens is the small amount of current will be flowing through the material. So this current will heats up the specimen and the temperature will rise. Okay, if I take a pin type insulator, okay, if I take a pin type insulator, so if any damages is present within that, a small amount of current will be flowing, instead of, even though your current can enter here, the small amount of current may flow from your conductor to the insulating material. So this current will be sufficient enough to rise the temperature within the insulator, and the heat generator is transferred to the surrounding medium by the conduction through the solid dielectric. So because of entire thing is a solid dielectric, so the heat will be transferred to the entire body of the dielectric by the radiation. Okay, so where the heat will be transferred to the outer surface, not the inner surface. So easily by the radiation, the heat will be transferred to the outer surface of the dielectric. So that heat generated under the electric stress is given by the equation here. So where W dc, so E square into rho, that is in terms of watts per centimeter cube, where rho is nothing but dc conductivity of a specimen. And similarly, if we consider for AC, it is given by E square F epsilon r tan delta divided by 1.8 into 10 power of 12, where F is frequency, del is a loss angle or dielectric medium, which was studied in the 5th module, that is loss angle or a dielectric of a dielectric material, and E is the RMS value. And heat, the heat which will be dissipated within the thermal, due to the thermal around the surface of the conductor, which is given by Wt equal to Cv dt by small dt plus div k grade into T. So here Cv is nothing but the specific heat of the specimen, and T is the temperature of the specimen, and K is the thermal conductivity of the specimen, and T is the time over which the heat is dissipated throughout the surface of the conductor. And the graph will explain here with respect to the two things here. So one, we have E1 and E2, the heat generated. Okay, so where E1 is a heat generated before discharge of heat within a surface of the conductor. E2 is a heat which has been discharged due to the leakage of current over there. Okay, and that heat will be, if you look at that, if you take a temperature T0, so this is a line where it has been given the T0 line. So if you consider that graph, then we'll get a TA and TB, the graph which will intersect with a E2, the heat generated, which will give a TA and TB, where TA is nothing but the temperature which has been generated due to the heat loss. So we say the heat has been lost, that will the difference will be TA minus TB, the heat loss within the entire part of your conductor, which will be given by TA minus TB. So at this time, whenever there is a heat loss, and hence the breakdown will occur in a solid dielectric because of a thermal breakdown. Okay, so whenever this heat generator is less than the heat loss, okay, the heat generated, so if you take that, this heat generator is less than the heat loss. In this case, the breakdown will occur. So this is regarding the thermal breakdown.